Hi, I am Professor Gudmundsson. This video is intended for my students in my aircraft design class at Embry-Riddle Aeronautical University, where I currently teach. The video presents excerpts from my textbook, General Aviation Aircraft Design, Applied Methods and Procedures. Its purpose is to supplement my class lectures. The book is available online from a large number of outlets, for instance Elsevier and Amazon. It is recommended for anyone interested in the design of general aviation aircraft. This video presents an example that combines aircraft navigation and the use of airspeed measurement theory. While not exactly a design problem per se, it still exemplifies situations that the student of aerospace engineering may be exposed to once in industry, and it is certainly one that I would expect the competent aerospace engineer being able to solve. So here is the problem. The pilot of a commercial jetliner is observing the onboard GPS during cruise on a standard day as it operates at pressure altitude of 35,000 feet on a heading of 45 degrees. He notices the airplane covers a ground distance of precisely 23 nautical miles in 3.5 minutes. The GPS also reports the winds aloft are 65 knots at 315 degrees. If this type of airplane has an instrument error of 1.5% indicated, determine the following characteristics: ground speed, true airspeed, equivalent airspeed, calibrated airspeed, indicated airspeed, all in knots, Mach number, true heading, and if the pilot wants to fly a true heading or ground track of 45 degrees, in what direction must the airplane actually be pointed? Let's begin by determining the ground speed in knots. This is a simple matter of dividing the distance covered, and denoted by delta S, by the time, converted to hours, and denoted by delta T. Since the distance is conveniently reported in nautical miles, the resulting number is in knots. Therefore, we have our first solution, 394.3 knots ground speed. The problem statement is presented in what I call the pilot universe. The purpose is to train aerospace engineering students in approaching the topic from that perspective. Next, let's review how directions are presented in the pilot universe. This differs in important ways from what students of engineering or physics are used to. First, consider the compass rose with which we are all familiar and in which north points upward, east points to the right, south downward, and west points to the left. The standard mathematical representation that we use assumes that 0 degrees is aligned with the east direction, 90 degrees points up north, 180 degrees points west, and 270 degrees points down south. For this reason, the orientation of increasing angles is counterclockwise. In contrast, the aviation world has the 0 aligned with the upward or north direction, 90 degrees means east, 180 south, and 270 points west. Consequently, the orientation of increased angles is clockwise. Therefore, a vector aligned 45 degrees in the mathematical representation is also at a 45-degree angle in the aviation representation. However, note how the axes of origin differ. Similarly, a vector aligned 135 degrees in the mathematical representation corresponds to 315 degrees in the aviation one. A vector at 225 degrees in the mathematical representation is also 225 degrees in the aviation one, and finally a vector aligned 315 degrees in the mathematical representation corresponds to 135 degrees in the aviation one. Now consider the orientation of the airplane given as 45 degrees in the aviation representation. This means the fuselage of the airplane is pointed at the angle shown. Note that points A and B refer to the motion the airplane would make in the absence of winds aloft. The airspeed indication system reacts to a dynamic pressure that corresponds to its true airspeed, which right now is unknown. Therefore, the true airspeed is a vector of unknown magnitude but known direction. Similarly, the airplane is operating in a mass of air that moves as indicated by the wind vector. That is, the wind is coming out of 315 degrees with a magnitude of 65 knots, and this would be knots with respect to the ground. This wind will cause the aircraft to drift southward, as shown here. For this reason, the track the airplane makes with respect to the ground, that is the ground track, is not directed along 45 degrees like the fuselage, but is aligned in some other direction, depending on the contribution of the wind, and which we don't know at the moment, but are expected to determine. The best way to treat the situation is to resolve the true airspeed, VTAS, and the wind speed, VWind, into their horizontal and vertical components. Thus, let's transform the vectors into a mathematical representation, as it will probably be easier for us to analyze. Here, the subscript north refers to northbound motion, and E to eastbound motion. Then, the complete motion of the aircraft with respect to the ground can be described as the sum of the true airspeed and winds aloft vector. This is the ground track vector. As stated earlier, the airplane will drift because the mass of air in which it is operating is moving over the ground. It is imperative to realize that as far as the aircraft is concerned, it is not yawed. Amazingly, examples exist of pilots cruising in such crosswind conditions, thinking they need to yaw the aircraft. Granted, it is a common piloting technique to yaw the airplane during approach to landing, something known as crabbing. However, I'm not talking about that. I'm talking about cruising, crabbed, in an attempt to maintain heading. Luckily for the rest of us, only a fringe of pilots does this, probably because of limited understanding of the fundamentals of navigation and aerodynamics. Yawing an airplane to maintain a desired heading is a terrible mistake that will only increase the drag of the airplane and excessively consume fuel. The only navigational trick that needs to be done is to point the airplane into a direction so it will now drift along the line between points A and B, in this example, rather than south of it. In this particular problem, the pilot only has to fly the airplane along some heading less than 45 degrees in the aviation representation. What exactly that heading must be will be calculated in a moment. Now let's set up a vector diagram for this problem. Note that all the unknowns are presented using a blue bold font. Next, let's solve the vector equations as shown. Substitute the known parameters and simplify. This leads to two equations with two unknowns, theta and VTAS. Now, to solve, subtract the bottom equation from the top one. This gives us a trigonometric relationship for theta. Unfortunately, it requires a bit of algebraic and trigonometric acrobatics to solve for theta. Start by squaring both sides of the equation, expand to get, gather terms. Then note the two trigonometric identities. Use them to simplify the expression, making it possible to solve for theta as follows. So theta equals 35.5 degrees. Recall that this value assumes the mathematical representation. I will show shortly what this looks like in a schematic. This allows us to solve for VTAS using either equation, as shown below. Therefore, we have determined that the true airspeed amounts to 380 knots, ktas. Let's update the vector diagram. We started with this, and now we have this. Now let's recap to see what we have completed so far. We have determined the ground speed, true airspeed, and the ground track along which the aircraft is moving. Then let's continue with the remainder of the problem. Now we have all the information required to evaluate the remaining airspeeds using the methods in my book. We do this as follows. Calculate density ratio using equation 16-7. Use it to calculate the equivalent airspeed per equation 16-26. Then calculate the calibrated airspeed per equation 16-28. We have to calculate the pressure at altitude P and the compressible dynamic pressure Q. We calculate the pressure at altitude using equation 16-16. Then compressible dynamic pressure is calculated per equation 16-29. Clearly, we must determine the Mach number, and this is done using equations 16-14 and 16-23, and by converting the true airspeed of 389 ktas into feet per second. Therefore, the compressible dynamic pressure is. We can now substitute all of these into equation 16-28 to get a calibrated airspeed of 225.7 kCAS. Then, knowing the calibrated airspeed, let's estimate the airspeed the pilot is likely to read on his airspeed indicator. This should be around 222 kS. We have now pretty much determined everything that was requested, except the last part. In what direction should the pilot point the nose of the airplane to fly a ground track of 45 degrees in the aviation representation? Or as they would say, what heading should be flown? To solve this, we must resort to vectors again. Given the points A and B, we desire to fly a heading that leads to a ground track along the line shown. This will be our ground track vector v sub gs. Note that in this problem, it must make an angle of 45 degrees with respect to the horizontal. We must account for winds aloft, shown as v wind. Note that here, it must make a negative 45 degree angle with respect to the horizontal. Therefore, our true airspeed vector vtas is the difference of the two. It makes an angle phi with respect to the horizontal. Then, we write the complete motion of the aircraft with respect to the ground, again as the sum of the true airspeed and winds aloft vectors. Substituting the known values into the previous vector equation again leads to two equations with two unknowns. Using a similar process as before to solve the two equations, we find that the new heading angle must be 54.65 degrees in the mathematical representation, or 35.35 degrees in the aviation representation. If you proceed in that manner, you will see that you must be careful when the mathematics lead to two solutions, and you must know which one to select. Remember that you can also solve it using algorithms such as regula falsi or the Newton-Raphson method. The resulting ground speed will then amount to 383.3 knots ground speed. We have thus completed the solution of this problem. I hope this video has helped you understand how navigation problems can be solved and some applications of airspeed measurement theory. If so, I hope you'll consider giving this video a thumbs up rating on YouTube. Thank you for watching.